And the last part here before we jump into these drugs is the structure and function of this GABA chloride ion channel that we can see right here. So just taking a first look at it, right, this is a GABA chloride ion channel, and thus the neurotransmitter is GABA. Now, I didn't mention this earlier because I didn't want to overwhelm you, but notice here that it's not just one GABA that needs to bind, but actually two GABAs need to bind in order to let an ion through here. So I'm just going to write a neurotransmitter times 2. What is this receptor called? Well, it's called the GABA-A receptor. And the reason it's called the GABA-A receptor is due to the type of subunits that comes through, comprises this channel, and also the ion that goes through it. And we'll talk about GABA-B on the next slide. What is the ion here? Well, the ion is chloride. And so what happens? Chloride comes into the cell, and it makes the inside of this cell slightly more negative. And the effect of that is an inhibitory postsynaptic potential. So let's put this all in context, because it's kind of confusing unless you see it all together. So let's just say here is my presynaptic neuron. Alright, and let's say here is my postsynaptic neuron. Now I'm going to draw this a little different than you might see it, because we're going to add something to it here in a second. So what's going on here? Well, I'm going to get a different color. So we have an action potential, right? It comes down the cell. We have this voltage-gated calcium channel. This allows calcium to come in, right? And so calcium comes in, and it causes the fusion of these vesicles. And what are these vesicles containing? They are containing GABA. And so from this presynaptic neuron, these vesicles traverse across the synaptic cleft, and they will bind to a receptor on the postsynaptic membrane. So let's just say here is the ion channel, here is the receptor. That's what we're looking at right here. That receptor is that one here. So here's step 1, action potential comes, 2, calcium comes in, 3, we get the fusion of GABA, and 4, it diffuses across, 5, it binds to this receptor, and that's what we're seeing here. And so 6 would be the chloride ions that are here coming into the postsynaptic neuron, causing an inhibitory postsynaptic potential. And so that's what we see right here. Now, this isn't the only neuron that's interacting with this postsynaptic neuron, right? We could also have an excitatory one that's synapsing here as well. So I'm not going to draw everything like I did before. But let's say we have all of these steps, but instead of GABA coming here, let's say we have, man, it's crazy how nice colors look. Let's say we have glutamate. That was a silly comment. And so with glutamate, right, it also binds to its own receptor, but in this case, let's say it lets sodium in, and now we have an excitatory postsynaptic potential. And so what this cell is doing is it says, okay, is there more positive or is there more negative? If there's more positive, is it enough to reach threshold? And if there is, then maybe I'll elicit another action potential here. And here are these, sodium channels on the axon that allow charge to come through. Remember, anywhere you block along this pathway, you can mess things up. So this can also be represented with a little diagram here. And so when I say that the sedative hypnotics have dose-dependent CNS depressant effects, this will kind of explain why. So right off the bat, we can, what's our color? Let's go back to orange. So here, let's say we had this excitatory stimulus. Let's say this was glutamate. It was enough to reach threshold. We kick off, boom, an all or none action potential, and we come back to resting membrane potential. But now we get this inhibitory stimulus. Okay, so this, let's say, is GABA. And this GABA caused a dip in this membrane potential. Now, the next time this excitatory stimulus comes along, glutamate, it is not enough to reach threshold, and as a result, we get this CNS depression. The depression is a result of no more communication or decreased communication. And so if this guy overwhelms here, we're not going to get this action potential, and therefore we're depressing the central nervous system. Make sense? All right, so let's take a moment and look at the receptors for the different neurotransmitters and drugs here. So the first thing you should notice is we have GABA here, we have the benzodiazepines here, and we have the barbs here. And so these are all binding at distinct locations. And if you can't tell from this kind of cross-sectional view, maybe a top-down view might be a little better. So we have GABA, which is the endogenous neurotransmitter, and by convention, the endogenous neurotransmitter typically binds to the alpha subunit. Here we have our benzodiazepines, represented with a BZ, and this binds to the alpha and gamma subunit that we can kind of see right here. This was alpha, this was gamma. And here we have our barbs, and our barbs are binding to the beta and gamma subunit. So what's important here is that they're not, the barbs and the benzos, they're not competing for the same binding site. And as a result, they can have additive effects. Okay, it's important to know that they're not competing. Also, there's a lot of heterogeneity even within this GABA receptor, this GABA-A receptor. And in particular, notice that the benzos are binding here, and this binding site actually has a name, and we call it the BZ1 receptor. And this is probably due to the fact that there's this alpha-1 subunit here. Now, the only reason I mention this, you don't need to memorize the exact molecular makeup of this ion channel, but some of our newer hypnotics are very selective for this BZ1 receptor with this alpha-1 subunit. Newer hypnotics are selective. And because of the location of these receptors, we can get these hypnotic effects, which is making you sleepy, without as much of the anxiolytic effects. And that's kind of one of the benefits of these newer hypnotics. So you get more hypnotic effect with less sedative effect. And we can see that right here. This is Ambien or Zolpidem. And the last point I want to make is not only do we have selectivity for particular binding sites, but also for ions. So this is the GABA-A chloride ion channel, right? But we also have a GABA-B channel, or GABA-B, potassium ion channel, GABA-B. And so unlike this, which allows calcium chloride to come into the cell, this GABA-B lets potassium out. And the drug that interacts most with this receptor is baclofen, which is a spasmolytic, baclofen. And you would use that for muscle spasms. And we probably won't talk about baclofen again, but it's just an important thing to note right here. Finally, one last point while we're looking here, we have this guy right here, flumazenol. And notice where it is. It's right here for between the benzos and the newer hypnotics, but nowhere near where the barbs are. And so what this is actually, it's an antagonist. Antagonist. Oh, I can't write it all out, but let's write it here. Antagonist. And so this is special in that is it can reverse the effects of overdoses from benzos or zolpidem, and won't have any effect on the barbs because they have different binding sites. So again, understanding the structure will really tell you the function of how these work. And that, my friends, is sedative hypnotics, the foundations. On a last little thing here are some questions that hopefully you should be able to answer having attentively watched these lectures. So it's learning the objectives with homework questions. Feel free to do these on your own.